Good morning, everyone. I'm glad to have the opportunity to present a research work focused on feature selection and machine learning in cybersecurity, entitled Feature Selection in Cybersecurity, a comparative study of machine learning models. During this presentation, we will share important concepts, recent findings, and practical applications that contribute to advancing this field. This presentation is structured as follows. We will begin with an introduction and provide some necessary background. Next, we will present the main categories of feature selection methods. Then, based on a recent literature review, we'll explore how machine learning models are applied in cybersecurity, followed by selected applications of feature selection in this field. Finally, we will discuss current challenges, outline future research directions, and conclude with final remarks. We will talk about the important role of feature selection and machine learning in the field of cybersecurity. These techniques are essential to protect data, maintain economic stability, and ensure digital sovereignty. Machine learning enables automatic and rapid threat detection through behavioral analysis and anomaly detection. However, their effectiveness depends on heavily on data quality and the types of attacks. Feature selection methods help tackle challenges such as computational complexity, overfitting, and also limited interpretability by reducing dimensionality and improving model efficiency. To give some background, feature selection is the process of reducing the number of input variables while preserving the most relevant information. This reduces noise in the data and prevents models from overfitting, which leads to better generalization and robustness. By focusing on fewer but more informative features, the training becomes more efficient and the resulting model more reliable. Feature selections. Feature selection methods fall into several categories depending on how they are applied. For example, filter methods are statistical criteria to evaluate each feature independently of learning model. Wrapper methods select features by iteratively training model and evaluating performance, while embedded methods incorporate feature selection as part of the model training itself. Finally, hybrid methods combine multiple approaches to leverage their strengths. The several machine learning models commonly used in cybersecurity. We're going to highlight some machine learning models in cybersecurity. For example, decision trees are simple and interpretable but prone to overfitting, especially with noisy data. Random forests are ensembles of trees that reduce overfitting and handle high dimensional data but are less interpretable. KNN is a simple, non-parametric method good for anomaly detection but computationally expensive on large data. SVM offer high accuracy when data is well separated, although they can be computationally costly and less effective with noisy data. For some most used evaluation metrics in cybersecurity, to evaluate these models' performance, several metrics are widely used. For example, accuracy measures overall correctness, but can be misleading with unbalanced data. Precision and recall balance detecting true positives while minimizing false alarms. The F1 score combines precision and recall for a balanced evaluation. Detection rate reflects the model's ability to correctly identify intrusions using these metrics helps us understand model effectiveness in real-world cybersecurity applications. Now we're going to cite some applications of feature selection methods in cybersecurity according to last works in this field. For example, for filter methods, it includes statistical techniques such as Z-score, which is a measure indicating how far a data point is from the mean or the mean in terms of standard deviations. Minimax scaling, which is a normalization technique that scale data on a fixed range, usually between 0 and 1. ANOVA analysis of variance, which is a statistical test used to determine if there are significant differences between group means. And we have also information gain, correlation, mutual information, which are metrics to quantify the relationship between variables. For example, for wrapper methods, it includes recursive features elimination, which is an iterative method that removes less important features based on model performance. For example, cross-validation, which is a technique to evaluate model generalization by partitioning data into training and testing sets multiple times. For embedded methods, we're going to cite some, for example, CNN-based methods, which is deep learning models particularly effective in feature extraction, and random forest-based methods, ensembles, models that provide feature importance scores during training. For hybrid methods, it combines multiple approaches, including optimization strategies like genetic algorithms or particle swarm optimization. For example, a genetic algorithm is an optimization algorithm inspired by natural selection. Particle swarm optimization is a population-based stochastic optimization technique. Of course, we will not go into all the technical details now, but these methods can help adapt feature selection to the complexity and variety of cybersecurity data. Now we're going to show some relevant improvements of application of feature selection methods in cybersecurity. Ongoing improvements focus on increasing model performance by selecting the most relevant features, reducing the number of features to simplify models, cutting down computational time, and enhancing interpretability so that security analysts or experts can better understand model decisions and, of course, take action. We're going to summarize some advantages and limitations in this slide. For example, filter methods are fast and simple, but miss complex feature interactions. Proper methods improve model performance, but are computationally expensive and often risk overfitting. Embedded methods select features during training, balancing efficiency and accuracy, but may reduce complexity or flexibility and interpretability. Hybrid methods and meta-heuristic methods combine different approaches to leverage their strengths, offering improved feature selection performance. However, they can be computationally intensive and require careful tuning to adapt to dynamic cybersecurity environment. Of course, choosing the right method depends on the specific cybersecurity problem and also on data characteristics. For discussion, we're going to show some utility trends and issues in this field. Feature selection clearly improves model efficiency and accuracy in cybersecurity. Current trends include integrating deep learning with feature selection and growing adoption of hybrid and meta-heuristic approaches. However, challenges remain. such as computational costs of wrapper and hybrid methods, lack of standard benchmarks or benchmarking datasets, and difficulties in adapting to evolving cyber threats. For future research directions, it include developing more scalable and adaptive feature selection algorithms, enabling real-time analysis, integrating explainability for transparency, and creating standard datasets and benchmarks to better evaluate and compare different methods in cybersecurity. To conclude, we're going to say that facial selection is a crucial tool to enhance machine learning models for cybersecurity, helping reduce complexity, improve accuracy, and increase interpretability. Despite challenges, ongoing research is pushing towards more adaptive, efficient, and explainable solutions to keep up with the evolving threat landscape. Thank you for very much for your attention. I'm happy to take any questions you might have. Please feel free to contact me afterward if you wish to discuss further.